Hey everybody, and welcome in. Welcome in. How's it going today? Sorry for a little bit of a late start there. Had to get everything all set up for us. So today we are going over the CompTIA Network Plus Chapter 4. This is our part 2. We'll see how far we get into it today. Chapter 4 is pretty long, and the next thing we're working on is binary to decimal and hexadecimal conversion. And I wanted to spend a pretty good amount of time just us going over practice examples for the binary to decimal and hexadecimal version because it was definitely something that we covered here in the study guide. And then when I went into subnetting, it was kind of like, ooh, I need a refresher again because I didn't really spend tons of time practicing it. So yeah, let's get into it. Otherwise, just finished up my introduction to networking class with college, so that's a huge relief off my shoulders. And I'm going to be taking a break from the college classes for a little bit because I want to hyper focus on the CompTIA Network Plus, A Plus, and Security Plus certifications for a few months, and then I'll probably bounce back in after about 2 months of taking a break, take a quick class because, that whole, hey, if you're not in school for 6 months, you have to start repayment. I don't want to do that. And then later this year, I have a vacation planned out. So don't want to be in the middle of a class while I'm on vacation. Anyway, yeah, let's just bounce into it. We'll start reading through the study guide and taking some notes. So get you guys over to the desktop. All right, we're a little jammed up right now, so let me get some of this stuff out of the way, and we'll put this guy over here. All right, so this is where we left off. If we're just going to do a quick recap on where we're at so far, we've kind of went over some networking basics on how Bob learns who Sally is, and when they're connected to a hub, what a hub will do for us. Let me zoom in a little bit more so that way we can actually read the information here. So this was Bob trying, his name was Bob, yeah. This was Bob when he was trying to learn who Sally was. Like, we know the name of the computer, but we don't know like the destination IP address and the destination MAC address, right? So Bob is going to send a broadcast over the network. And remember, our broadcasts ends in 255. That's the IP address that we're going to be using is when we have our IP address. If it ends in 255, that's going to be the broadcast IP address for that network. And another thing to keep in mind with broadcasts is it can be in all Fs. In all Fs. So Bob's going to be like, hey, I want to find out Sally's name. Our NBNS was our NetBIOS name system, if I recall correctly. And then he's going to send this out. This is his source IP address, his source MAC address. And so what we're going to be learning today is how to convert this into binary, right? So we have this BE, and then we have this D here. And we're going to be learning how to convert like 14 into binary and all this stuff. Okay, so Bob sends out his broadcast of all Fs, and check this out. This is what it looks like. So yeah, the next thing Bob has to do is broadcast on the LAN, the local area network, to get Sally's MAC, which is Media Access Control address. Remember, the MAC address is that burned in address into the network interface card, or the NIC. The network interface card is where our Ethernet plugs into in the back of our computer. So we have an address resolution protocol broadcast of, hey, this is Bob. who has this IP address, tell this IP address. And this is Sally's response. She's like, hey, this is me. I'm sending this back to Bob for address resolution protocol. My IP address is this MAC address. And then we have the second part of, this is Sally again talking to Bob. The NetBIOS name system name query response is the answer to his question. And then we went over some Ethernet basics. We went into Cisco Packet Tracer, and then we set up a collision domain. Remember, a collision domain is a place where when we have a network set up, there is room for two signals to go and hit each other. And then we went over a broadcast domain. We can see that switches will break up a broadcast domain, routers break up a broadcast domain. Then we went into the carrier sense multiple access with collision detection and how that works. So if there's a collision that's detected, so we can see here computer A, computer D are sending out a signal at the same time. We have a collision on the LAN. What we'll do is we'll send out a jam signal. That jam signal tells the computers, hey, you need to start a timer. And after the timer expires, then they can begin to transmit again. We went over broadband versus baseband and how broadband will allow us to have different frequencies traverse the same line. So if we have like an Ethernet cable, it'll be different frequencies in electricity that's going down the line. If we have like fiber optics, it'll be different frequencies of infrared lasers that go down the line. We touched base on baud rate versus bit rate, just a way of measuring how much data is going down the line. We went over what we were talking about with different frequencies. The different frequencies, just a change in the wavelength. We have different types of wavelengths. But if you can imagine, if we had a straight line going through here, right in the middle, and then a straight line going through right in the middle, you can see if we were to take this wavelength and combine it into this, we'd have two different frequencies over the same line. And the way that we go about turning that into binary is we adjust the amplitude. The amplitude is the distance from the line to the peak and the trough. So that's how we go about changing what that frequency represents. We adjust the amplitude. We talked about half versus full duplex. So half duplex is just when I can talk in one direction at a time. So I can send, then I'll wait, and then I can receive. Full duplex is when we can send and receive at the same time. Half duplex requires at least one pair of wires, so 2 wires in total. Full duplex requires at least 4 wires. So that way we can send and receive at the same time. Then there's simplex as well, which wasn't covered here, but simplex is when I can only talk in one direction or I can only receive. Okay. Then we went over some stuff with how we can configure computers to run at full duplex and then like what speed they can go at. Then we talked quickly about Ethernet at the data link layer with this paragraph, and now we're on to binary to decimal and hexadecimal conversion. So that's just a summary of where we left off. My goal again today is to take a pretty decent amount of time to go over what's taught in the book and then do some examples from ChatGPT with them giving us some hexadecimals to work on converting. So that's what we got today. And this is CompTIA Network Plus Chapter 4. I would just call this Part 2. And depending on how good we're doing and how comfortable we are, we may finish up Chapter 4 today. But we'll play it by ear. Not wanting to spend a long time on stream today doing this. Kind of want to reward myself, and I bought Pragmata, so I want to play that. So we might go into that after a little bit. So let's get into it and get my notes all set up, get my spectacles on. Staring at screens every day, all day isn't good for your eyes. And get my tablet up here so I can take notes as we need to. Let's just refresh Ethernet at the data link layer. Ethernet at the data link layer is responsible for Ethernet addressing, commonly referred to as hardware addressing or MAC addressing. Ethernet is also responsible for framing packets received from the network layer and preparing them for transmission on the local network through the Ethernet connection media access method known as CSMA-CD. And that's one of our acronyms that we're going to keep using throughout here. So let's just get our Word document up so that way we can start tracking these. CSMA CD, which is carrier sense. Drawing the blank. The coffee hasn't fully kicked in. I just woke up. Carrier sense multiple access. Yeah. Multiple access with collision detection. And we'll scroll back down. Ethernet MAC addresses are made up of hexadecimal addresses. So before I discuss MAC addresses, let's start by talking about binary, decimal, and hexadecimal addresses and how to convert one to another. So binary to decimal and hexadecimal conversion. Understanding the difference between binary, decimal, and hexadecimal numbers and how to convert one format into the other is very important before we move on to discussing the TCP/IP protocol stack and IP addressing. So let's get started with binary numbering. It's pretty simple, really. Each digit used is limited to being either a 1 or a 0, and each digit is called 1 bit, short for binary digit. Typically, you can count either 4 or 8 bits together, with these being referred to as a nibble and a byte. So when we have, actually we'll just put that in a Word document. So we have 4 bits is a nibble, and 8 bits is a byte. So what's interesting about binary numbering is the value represented in a decimal format. The typical decimal format being the base 10 number scheme that we've all used since kindergarten. The binary numbers are placed in a value spot, starting at the right and moving left, with each spot having double the value of the previous spot. Then we have a table that shows the decimal values of each bit location in a nibble and a byte. Remember, a nibble is 4 bits and a byte is 8 bits. In network addressing, we often refer to a byte as an octet. Mathematically, octal addressing actually refers to base 8, which is completely different from the base 10 we are familiar with. So, technically speaking, we are using the term incorrectly, but it's the common usage anyways. When we get to Chapter 8, IP subnetting, troubleshooting IP, and introduction to NAT, which is network address translation, you will see that I'll use byte and octet interchangeably when discussing IP addressing. So table 4.1, binary values. So we have nibble values, and then we have byte values. That's something we're going to write down over here. All right. So remember, we have our nibble. We have our nibble, which can have 4 bits. So the values of those bits can be 8, 4, 2, and 1. And then we have our byte, which has 8 bits. Let me get the mic a little further away from my face. We have 1, 2, 3, 4, 5, 6, 7, 8. And that can be 128, 64, 32, 16, 8, 4, 2, and 1. So what this all means is that we have that if a 1 digit is placed in a value spot, then the nibble or byte takes on that decimal value and adds it to any other value spots that we have a 1. If a 0 is placed in a bit spot, you do not count that value. Let me clarify things for you. If we have a 1 placed in each spot of our nibble, we then add up 8 plus 4 plus 2 plus 1 to give us a maximum value of 15. Another example of our nibble value is 1010, which means that the 8-bit and the 2-bit are turned on and equal in decimal value of 10. If we have a nibble binary value of 0110, then our decimal value becomes 6 because the 4 and 2 bits are turned on. So let's work on that for just a second. We'll go ahead and put the Word document here. So we'll start with his first example, what he means. So I have the binary code of 1010. And what he's talking about is we have the 8, 4, 2, and 1. That value doesn't change, okay? We're talking about a nibble right now. So all we have to know is that let's just do this. A, B, C, and D. Make it a little bit easier, right? So A, its spot is always going to have the value of 8. B is always going to have the value of 4. C is always going to have the value of 2. And D is always going to have the value of 1. So what he's talking about is when we're converting a binary nibble into a value, if we want to turn on the value, so that way we're going to add it, we would utilize a 1. If we want to turn off the value so we won't add it, we utilize a 0. So with the example of 1010, we have turned on the value of 8. The value of 4 is turned off. The value of 2 is turned on. The value of 1 is turned off. So we drop down the 8, then we add the value of 2 because the values of 8 are turned on and the values of 2 are turned on. So 8 plus 2 would equal 10, and that's all we're doing. So A will always be a value of 8, B always a value of 4, C always a value of 2, D always a value of 1 for our nibble. And then our next example was 0110. We got our value of 8, 4, 2, and 1. If we look and see, 8 is turned off, 4 is turned on, 2 is turned on, and 1 is turned off. So we take our value of 4 and our value of 2. 4 plus 2 would equal 6. And that's what we're doing with our nibble. If we turned all of them on, if we have 1, 1, 1, 1, this is our nibble right here. That means we have 8, 4, 2, and 1 all turned on. And when we add them together, we get 8 plus 4 equals 12, plus 2 is 14, plus 1 is 15. So we get a value of 15 for our nibble. And then if everything's turned off, we have a value of 0. If everything is turned off, if we have 0, 0, 0, 0, that equals 0. So that's what he's talking about there. So that's how we convert binary into a decimal. Binary into a decimal. Now with a byte, we're just adding more values. We can see over here, that's our nibble, right? Well, a byte has 8 values. So we just come up to 128. All right. And you can kind of notice a habit here, a behavior here, right? 128 and then 64. 64 is half of 128. 32 is half of 64. 16 is half of 32. You can kind of see the behaviors here, right? 8 is half of 16. 4 is half of 8. 2 is half of 4. 1 is half of 2. So that's kind of how it's set up. And if we were to do the same thing with a byte, let's just give us the value of 0 or 1, 0, 1, 0, 1, 0, 1, 0. Right? That's 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have the value of 128, 64, 32, 16, 8, 4, 2, and 1. So we're going to drop down our 128. We're going to drop down our 32. We're going to drop down our 8. And we're going to drop down our 2. And we're going to add them all together. So let's see. 128 and 32. So 160. And then 160 plus 8 is 168. Plus 2 is 170. So that's all we're really doing here. If a value is turned on, we add the number. If it's turned off, we don't add the number. So that's how we go from binary to decimal. So binary to decimal. If a value in the bit for a byte or nibble, and no, I don't know who named these things, are turned on, with a 1, they are added. Okay. Sweet. I think we can conceptually understand how we would take a nibble and a byte, and depending on what binary value we have for that nibble and byte, we can easily convert it to a decimal number. Because all we're doing is we're taking whatever values are turned on, and then we are adding them together to get an ultimate value. All right, this was what, 170? Let's see. Yeah, that was 160 plus 8 plus 2 is 170. All right. And the same thing goes if we had like 0, 0, 0, 0, 0, 0, 0, 1. Like the entire byte would have a value of 1. That's the only thing we're adding. Everything that's 0, we aren't adding. All right, so that is binary to decimal. Binary to decimal. Let's move on to the next thing. Okay, but the byte values can add up to a value that's significantly higher than 15. This is how, if we count every bit as a 1, then the byte and binary value looks like this. Remember, 8 bits equal a byte. So we have a value of 1111111111111. Yeah, there we go. And we're going to start to see a number that looks kind of familiar, like it should kind of itch something in your brain. We then count up every bit spot because each is turned on. It looks like this, which demonstrates the maximum value of a byte. So if we have a byte and we have every value turned on, I'm going to move down a little bit. If we have a byte and the value is 11111111, and we add everything together, which is the 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, we get a value of 255. All right. Now, if we were paying attention a little bit ago when I was talking about stuff, we should have a little itchy feeling in our brain, like, that number looks familiar. And you're absolutely right. That number does look familiar. When we scroll up in our study guide, and we look at when Bob was talking to Sally. See how that ends in 255? We have a hint at something in the future. But yes, when you add a whole byte together that has the values of the entire byte turned on, we get a value of 255. Okay? A binary number can equal plenty of other decimal values. Let's work through a few examples. So, I'm not going to cheat. 1 second. I'll be right back. All right, we're back. Man, nothing wants to cooperate with me today. Yeah, it's getting kind of hot in the room, so I had to turn on the air conditioning, and then, sure, my text notifications aren't coming over. Sorry about that. All right. And then, yeah, of course, the camera that follows me likes to lock in on weird places like my closet. Yeah, one of those days. All right. Let's go ahead and transition over back to the desktop. All right. So where were we? So we were going to work on the example of a binary number can equal plenty of other decimal values. Let's work through some examples. So we're going to work on this example, and we're not going to cheat. Cover that up before I look at it. Still haven't looked at it. We haven't cheated yet. So he gave us a value of 1001, 1001, 0110, 0110. So we have 128, 64, 32, 16, 8, 4, 2, and 1. So 128 is turned on, plus 16 is turned on, plus, and let me know if that air conditioner is too loud or annoying. Doesn't look like it's spiking my audio, so I think we're okay. Plus 4, plus 2, and that's what we have. We have 4 values turned on, 128, 16, 4, 2, and that's what we have. So 128 and 16, I'm going to cheat. So 16 plus 4 plus 2, we have 22. So 128 and 22, 0, 1, 5. So we have a value of 150 if we add this all together. So if we have the byte of 1001, 0110, we can add those together to get a value of 150. So let's uncover that. And yes, 128, 16, 4, and 2 equals 150. So which bytes are on? Oh, it already gave us the answer there. That's kind of lame. But let's just work through the example. We have 0110, 0110, 1100, 1100. So we have 128, 64, 32, 16, 8, 4, 2, and 1. So we see that we have 64 plus 32 plus 8 plus 4. So 8 and 4 is 12. 32 plus 12 is 44. 64 plus 44. Let's see, 44. We have 8. So we have 108. Yes, we have a value of 108. So which bits are on? If we're going with his example, right here, he's saying that the values 128, 64, 32, and 8 are on. So what does that look like for us in binary? We have 128, 64, 32, 16, 8, 4, 2, and 1. 128 is turned on. 16 is turned on. 4 is turned on. And 2 is turned on. The rest are zeros. So we have 1, 0, 0, 1, 0, 1, 1, 0. That would be our binary. And then if we were to add those up, 128 plus 16 plus 4 plus 2, let's see, 16 plus 6 is going to be 22. And 128 plus 22 is, let's see, 148, 150. Right? I messed something up here. Where are we at? Oh, I went back up and read the wrong thing, huh? There we go. So let's work on this one. We have the values of 128, 64, 32, 16, 8, 4, 2, and 1. 128 is turned on, 64, 32, and 8. So our binary value here is 1110, 1000. That's going to be our byte. And then we have 128, 64, 32, 8. So 32 and 8 is 40. 40 plus 64 is 104. So 128 plus 104 is 232. All right? Yes, 232. Public math, scary. So this is a really interesting table right here, especially for subnetting. This table is very interesting because it's like, I don't want to go too much in depth, but if you look at an IP address of, let's just think of like 192.168.x.x, right? So we'll have like the network ID, and there's different classifications of networks, and we'll definitely get into that. But like for now, if we focus on, we have the network ID, and then like the user ID. These two octets are like what we use to provide a value to our user. And this binary table here will really help us out with subnetting in the future. So that's good to hold on to. All right. So the next thing we're going to move on to are hexadecimal addressing. Hexadecimal addressing is completely different than binary or decimal. It's converted by reading nibbles, not bytes. By using a nibble, we can convert these bits to hex pretty simply. First, understand that the hexadecimal addressing scheme uses only the numbers 0 through 9, and because the numbers 10, 11, 12, and so on can't be used because they are two-digit numbers, the letters A, B, C, D, E, and F are used to represent 10, 11, 12, 13, 14, and 15 respectively. So this is how we go about using the nibbles to count up to 15. And we can see how, we get F, we get E, and these nibbles can represent different values in our octets. When we're talking about like a MAC address. I also started noticing that I didn't hit record, so that's awesome. One second, let me text the lady back. Sorry about that. All right, let's work on hex to binary conversions. Okay, we'll make some new space on here. And just want to spend a little bit of time on this one and then work through a few examples. So we have our hexadecimal value, our binary value, and then the decimal value. Remember, the decimal value is just if we were to add all the values together, what number do we get at the end? Okay. And then the hexadecimal value, you'll see that everything up to 9 is exactly the same. The only difference is when we get to a value of 10, we have A. A value of 11, we have B. Value of 12, we have C, 13, D, 14, E, 15, F. Okay? So, let's see. Let's go up and look at Bob's MAC address. And see what Bob's MAC address would be in binary. All right? I think that'd be like an interesting little experiment. Let's go back up here to Bob. Where are you at, Bob? Okay, so here's Bob's MAC address. Bob's MAC address is 0014 22 BE 18 and 3B, right? Well, not in reality. It's 0, 0, then 1 and 4, then 2 and 2, then B and E, then 1 and 8, then 3 and B, right? And we have 2 nibbles in each of these, right? 2 nibbles in each. So this octet is a byte. This 0, 0 is a byte. So we've grabbed up Bob's MAC address. Let's go back down to our table and let's convert it out to binary. It's going to be a long number. Okay, we have 0 and 0. So 0 and 0. 0, 0, 0, 0. First nibble. Second nibble is 0, 0, 0, 0. That one was pretty easy. Okay, then we have 1. All right, we have the 1, which would be 0, 0, 0, 1. So 1 and 4 equals 0, 0, 0, 1. And then our 4 would be 0, 1, 0, 0. 0, 1, 0, 0. So that's how we get the 1 and the 4. So 1 we saw up here, and then 4 we saw right here. And we're just kind of copying the numbers over right now, right? All right, now we have the 2 and the 2. So what is 2? 2 and 2. Really got to figure out something to do with the mic. It's always in the way of like trying to read, which is 0, 0, 1, 0. And then we repeat it, 0, 0, 1, 0. All right. Now we have the B and E. So if we go to B, B, E, we have 1, 0, 1, 1 for B. So that's the B nibble. And then for E, we have 1, 1, 1, 0. 1, 1, 1, 0. Hey, how's it going today? Welcome. So that's our B and our E octet. And then we have 1, 8. Our 1 is going to be the nibble, 0, 0, 0, 1. And then our 8 is going to be the octet. I'm sorry, the 8 is going to be the binary of 1, 0, 0, 0. And then our last one is the octet of 3B. So our 3 that will be the nibble 0011, and B will be the nibble 1011. So looking at Bob's whole MAC address, we have all of our nibbles broken down into bytes. All right, so we have the nibble 0, the nibble 0, the nibble is represented by 0000, and then the other one is 0000. That creates our byte for that octet. This is our octet. This is the byte for the octet of all zeros. Our next one, we have the nibble for 1, which is 0001, and then our nibble for 4, which is 0100. So those two nibbles together make a byte, and that byte would look like this, and so on. So that's what it would look like if we were to convert Bob's MAC address into binary. So let's go back into the study guide. He says, did you notice that the first 10 hexadecimal digits 0 through 9 are the same values as the decimal values? If not, look again. This handy fact makes those values super easy to convert. So suppose you have something like this, 0x6a. Some manufacturers put the 0x in front of the characters so you know that they're a hex value, while others just give you an H. It doesn't have any other special meaning. What are the binary and decimal values? To correctly answer that question, all you have to remember is that each hex character is one nibble, and two hex characters together make a byte. To figure out the binary value, first put the hex characters into two nibbles, and then put them together into a byte. 6 equals 0110, and A, which is 10 in decimal, equals 1010. So the complete byte is 0110, 1010. To convert from binary to hex, just take the byte and break it into nibbles. Here's how you do that. Say you have the binary value of 01010101. So let's do that before we read ahead and cheat and get the answer. So we have the byte of 01010101. So we may think, oh, we want to go and do the binary conversion of 128, 64, 32, 8, 4, 2, and 1. But remember, when we're talking about hexadecimals, we're going to break this into two nibbles. So our first nibble is 0101, right? So if we look at our table of 010, let's find the actual one, 0101, we see that we have 5. Another way we could do that is 0101. Remember, for a nibble we have 1, 2, 4, and 8. 8 is turned off, so we don't add that. We're going to add 4 because the value of 4 is turned on. 2 is turned off, so we won't add that. But 1 is turned on, so we'll add that. And 4 plus 1 will equal 5. So we have 5 for that nibble. And the other nibble, 0101, is also 5. So in hexadecimal, we have 5, 5, right? If I did that correctly. First, break it into nibbles, 0101 and 0101, with the value of each nibble being 5. Because the 1 and 4 bits are on, this makes the hex answer 0x55. And in decimal format, the binary number is 01010101, which converts to 64 plus 16 plus 4 plus 1 equals 85. So what he's talking about is that if we broke it into nibbles, our answer is going to be 55. If we were to only convert it via the binary conversion value, and we have 0, 1, 0, 1, 0, 1. Oh, I messed something up. I missed 16. 32, 16, 8, 4, 2, and 1. 0, 1, 0, 1, 0, 1, 0, 1. So 128 is turned off. We don't add that. 64 is turned on. 32 is turned off. 16 is turned on. 8 is turned off. 4 is turned on. 2 is turned off. And 1 is turned on. So 64 plus 16 plus 4 plus 1. That would be 10 plus 5, which is 15, 5, 1, 6, 7, 8, 85 equals 85. Public math scary. Okay, so now try another binary number. So if we were to take this and convert it to binary versus converting it into hex, we'd have two different answers. So let's work on our hexadecimal answer first. So we know our hexadecimal values are, if we were to go to 8, 4, 2, and 1. Remember, we have A, B, C, and D. These are our different bits, right? Our binary value is 1100, 1100. So our nibble 1 would be 1100, and nibble 2 would be 1100. So we have A, B, C, and D. So we see that A is turned on and B is turned on. C and D are both turned off. And then we'd add 8 plus 4 to get 12. All right, that's our decimal value. But for 12, we're going to represent that with the letter C. So we have the letter C. And then this one is exactly the same. The values of 8 and 4 are turned on. So we add those to get the value of 12. And that gets us the character of C. So this, if we converted to hexadecimal, we get the decimal value of 12 and 12, which would be C and C. And then if we were to convert that into a binary value, we have 128, 64, 32, 16, 8, 4, 2, and 1. Byte value in total. So we're not breaking it into two nibbles. We're just talking about the byte itself. We have on, off, off, on, off, off. So 128 plus 64 plus 8 plus 4. Let's see, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 plus 8, 24, 4 and 2, 0 in there. So 204 would be the value for this if we looked at it as a byte. That's the byte value. And then if we were to convert it to hexadecimal by breaking it up into two nibbles, we have C and C. All right. Now, what was that example? 1100. There we go. So our answer is 1100 equals 12 and 1100 equals 12. Therefore, it is converted to CC and hex. The decimal conversion is 128 plus 64 plus 8 plus 4 equals 204. Ooh, I didn't get that wrong. Nice. One more example, and then we're ready to get working on the physical layer. Suppose we're given the following binary number. All right, we have 10110101. So first we're going to work on hexadecimal. So we have 1, 0, 1, 1, 0, 1, 0, 1. So our nibble 1 equals 1, 0, 1, 1. And then nibble 2, 0, 1, 0, 1. Our nibble, remember, is A, B, C, D, 8, 4, 2, and 1. In our first nibble, we have 8 turned on, 2 turned on, and 1 turned on. So 8 plus 2 plus 1 equals 11. All right, that's our nibble converted to decimal. So nibble 1, decimal. And then our decimal to hex. Remember, we go up to 9. 10 is A, 11 is B. So hex would be B. So our nibble 2 to decimal. Our values of 4 and 1 are turned on. So 4 plus 1 equals 5. And then 5 converted to hexadecimal is 5. So we have B5. All right. And then if we're going to work on converting the byte itself into a value, the whole thing is 1, 0, 1, 1, 0, 1, 0, 1. We have 128, 64, 32, 16, 8, 4, 2, and 1. So we have 128 plus 32 plus 16 plus 4 plus 1. Let's try to do some quick math. 21. 32 plus 21 is 53. So 53 and 128. Let's see, that's 181, I think. Ooh, we made it. All right, so we have the answer is B5. 1011 converts to B, and 0101 converts to 5. The decimal equivalent is 181. All right, so I hope we're all feeling pretty good about that. What is nibble? Okay, so when we're talking, we'll move back up here. We're going to talk about a MAC address real quick. So when we were looking at our earlier example of having Bob trying to talk to Sally, one thing that he's going to use there is his MAC address. And here's an example of his MAC address, which is 001422BE18 and 3B. A nibble is what we use to identify a hexadecimal value. All right. So if we were to think about a byte, which has 8 total bits to it, a nibble is exactly half of that. It's half of a byte. And we can take a byte and use it to represent 2 hexadecimal numbers by converting them into nibbles. So if a byte has 8 bits in total, like this is a byte. And what we're doing is we are, instead of counting the whole thing together, we're breaking it into 2 pieces called nibbles. That's what a nibble is. And then these nibbles can be converted through hexadecimal to get values like B and 5. So this byte right here has a hexadecimal value of B5, or you can just do the binary conversion to get the number of 181. All right. So that's where we are with hexadecimals and binary conversion. Hope we're all feeling pretty good about that. I guess we don't really need to stomp this one into the ground. I think what we'll do is we'll just reassess and refresh hexadecimals as we get into subnetting, because I think that'll be more useful there. And we're going to go ahead and end the stream today. I know it wasn't super long, but that's one thing I wanted to cover in a whole video was hexadecimal and binary conversion. So yeah, hope you all have a good rest of the night tonight. If you're interested in kicking over to the gaming channel, I'm going to be playing Pragmata tonight just because I finished college and it's like a little reward to myself. Yeah. Any other questions before I bounce off there? About hexadecimals, binary, uh, nibbles versus bytes? Anything I can touch base on? And we'll pick up the conclusion of chapter 4 in the next video. Yeah, I think overall we'll probably just refresh hexadecimals and bytes when we get into subnetting, because subnetting is a little bit further in the book, and it's always good to refresh those things. Yeah, next we're going to be getting into Ethernet addressing and then the way the frames are set up. And that's when we'll conclude chapter 4, which I plan on doing tomorrow. But let's see. All right, I think I'll wrap it up there. Thank you so much, and have a good night tonight. Y'all take care. And once again, if you're interested, I'm going to be bumping over to the gaming channel to play some Pragmata. So I'll catch you next one.